In this lesson, we're going to cover limits of indeterminate forms and also L'Hopital's rule. First, we're going to consider the following limits. If you're given the limit as x goes to 1 and you have x squared minus x over x squared minus 1, if you were to use direct substitution property and plug 1 right in at first, you would get 0 over 0. But it's okay because you could factor this, cancel the common factors, and be able to simplify it. If you have this limit and you're trying to evaluate it, you would get sine of 0, which is 0, divided by 0, which would be 0 over 0, but you could use the limit theorem where this is equal to 1. Finally, if you were to get a limit like this and you were to evaluate natural log of 1, you get 0, and then the denominator is also 0. But at this point, you wouldn't be able to manipulate it to be able to evaluate the limit. So we're going to use a process called L'Hopital's rule. Here we have L'Hopital's rule. It says suppose f and g are differentiable and g prime of x is not equal to 0. Suppose that, and we have two limits. The limit as x goes to a of f of x equals 0, and the limit as x goes to a of g of x equals 0. Or let's say you have the same limits, but one is equal to plus or minus infinity, and the other one is also equal to plus or minus infinity. Then the limit as x goes to a of f over g is an indeterminate form of either type 0 over 0 or plus or minus infinity over infinity. And if that's the case, then you can apply L'Hopital's rule, which says taking the limit of a quotient of functions is equivalent to the limit of their individual derivatives. Okay, so we're going to evaluate these limits using L'Hopital's rule. This first one says the limit as x goes to 1, we have ln of x over x minus 1. We're going to check the limit of the numerator and the limit of the denominator. So here's your graph for natural log of x. When you take the limit of the numerator, you get 0. And when you take the limit of the denominator, you also get 0. So this limit is going to be of indeterminate form of type 0 over 0. Therefore, we can apply L'Hopital's rule. So we're taking this limit and it's going to be equal to the limit as x goes to 1. And then what we're going to do is we're going to take the derivative of the numerator. The derivative of ln of x is 1 over x. The derivative of the denominator is just 1. And I put a little h over the equal sign so that I know from here to here is where I applied L'Hopital's rule. So 1 over x divided by 1 is just the same as 1 over x. And then finally, the limit as x goes to 1 of 1 over x, you can take this 1 and plug it in by the direct substitution property, and we get 1 as our final answer. For this example, we have the limit as x goes to 0 of cosine of x plus 2x minus 1 all over 3x. So we're going to check this limit by taking the limit of the numerator and the limit of the denominator. When we're taking the limit of the numerator, we're going to go limit of cosine plus the limit of 2x, and then minus the limit of 1. The limit as x goes to 0 of cosine of x is 1. The limit as x goes to 0 of 2x is going to be 0, and the limit as x goes to 0 of this constant is just the constant. So we end up getting 0. Next, we take the limit of the denominator. So the limit as x goes to 0 of 3x is going to equal 0. Therefore, this limit is of indeterminate form of type 0 over 0. Therefore, we're going to apply L'Hopital's rule. So we're going to apply L'Hopital's rule, and I put an h over the equal sign so that I know that I'm applying L'Hopital's rule in this step. So we're going to take the derivative of the numerator and the derivative of the denominator. And again, I want to make sure everyone understands you're just taking the derivative of the numerator and you get negative sine x plus 2, and then you're just taking the derivative of the denominator and you're getting 3. Again, we're not doing like the quotient rule or anything. We're applying L'Hopital's rule, which says that this limit of these two functions is equal to the limit of their individual derivatives. At this point, we can evaluate our limit when we do limit of the numerator and the limit of the denominator. The limit of negative sine of x as x goes to 0 is going to be 0. The limit of 2 is going to be 2 because it's a constant. The limit of 3 is going to be 3. So our final answer is 2/3. For this example, we have the limit as x goes to infinity of ln of x over the square root of x. So I have the graph for ln of x and the graph of square root of x. So as x goes to infinity, you can see that this graph is going to keep growing without bound. And then also as x goes to infinity, this graph will do the same. It's going to grow without bound. So we take the limit of the numerator and we get infinity. We take the limit of the denominator, we also get infinity. So this limit is of indeterminate form of type infinity over infinity, so we can apply L'Hopital's rule. So we take the derivative of the numerator, which is 1 over x. For the derivative of the denominator, remember this is x to the 1/2. So here we get 1/2 x to the negative 1/2. So I rewrote this as 1 over x, and then this right here I rewrote it as 1 over 2 root x. Now we're going to copy, dot, and flip this. To simplify this, we're going to think of this as x to the 1/2. This is x to the 1. So when you're dividing same bases, you subtract their exponents. So x to the 1 minus x to the 1/2 is going to be x to the 1/2 in the denominator, and then I rewrote it as the square root of x. So next we have the limit as x goes to infinity of 2 over root x. And you're thinking about it as x is getting larger and larger without bound. So at first you're doing 2 divided by the square root of a small number, then it's going to be 2 divided by a bigger number, and then 2 divided by a bigger number. So as x grows without bound, this fraction is going to get infinitely small, so we say that the limit goes to 0. And that's our final answer. For this example, we have the limit as x approaches pi from the left of sine of x over 1 minus cosine. So I drew sine and cosine so that we could look at the graphs as x approaches pi from the left. Right here on sine, as x approaches pi from the left, we're reaching a height of 0. And then right here for cosine, as x approaches pi from the left, we're reaching a height of -1. So that means the limit of the numerator is going to equal 0. And for the limit of the denominator, you get 1 minus -1, which equals +2. So this is not of indeterminate form. So for evaluating this limit, we're not going to apply L'Hopital's rule. We're just doing the limit of the top and the limit of the bottom, and you get 0 over 2, and that just equals 0. So our final answer is 0. For this example, we have the limit as x goes to infinity of e to the 3x over x squared. So I drew both graphs, e to the 3x and x squared, and you can see as x gets larger and larger in the positive direction, both graphs are going to grow without bound. The limit of the numerator equals infinity, the limit of the denominator also equals infinity, so this is of indeterminate form infinity over infinity, and we can apply L'Hopital's rule. The derivative of e to the 3x is going to be e to the 3x, and we chain rule. We times by the derivative of the inside function, which is going to be 3, and the derivative of x squared is 2x. So now we have the limit of 3e to the 3x over 2x, and the limit of the numerator and the limit of the denominator also still both equal infinity, so this is still of indeterminate form infinity over infinity, and we're going to apply L'Hopital's rule again. The derivative of 3e to the 3x is just itself, and then we chain rule. The derivative of the inside function is 3. So we get 9e to the 3x over 2. So now we have a function in the numerator and a constant in the denominator. Since x gets larger and larger, and then in the numerator is where you have your function, the denominator is the constant, that means this entire fraction is going to grow without bound. So our final answer is going to be infinity. This example says the limit as x goes to infinity of ln of x quantity squared all over 4x. And again, I drew the graph for ln of x. When you take the limit of the numerator, it's going to equal infinity because the graph is going to grow without bound, so then when you square that, it's going to continue to grow without bound. When you take the limit of the denominator, you also get infinity, so this limit is of indeterminate form infinity over infinity, and we can apply the L'Hopital's rule. To take the derivative of the numerator, we're going to use the chain rule, so we're going to bring the 2 to the front, leave the inside the same, subtract 1 from the exponent, and then we're going to times by the derivative of the inside. The derivative of ln of x is 1 over x. And then we take the derivative of 4x and we just get 4. The 4 and 2 reduce. And then I rewrote this as ln of x over x, and then we times by, instead of 2 over 1, you times by 1 over 2. So we get ln of x over 2x. The limit of the numerator is infinity, and the limit of the denominator is also infinity, so this is of indeterminate form, infinity over infinity, and we're going to apply L'Hopital's rule again. The derivative of ln of x is 1 over x, the derivative of 2x is 2. So again, we're going to copy, dot, and flip, and you get the limit as x goes to infinity of 1 over 2x. At this point, you're going to consider this fraction, x gets larger and larger without bound, so 1 divided by a larger and larger number is going to equal 0. So our final answer is 0. Next, we're going to look at converting indeterminate products to indeterminate forms. It says we can convert a product to an indeterminate form. So if you have a product, you can leave one function on top, and then you can divide by 1 over the other function, or vice versa over here. Then it will be of indeterminate form of type 0 over 0, or plus or minus infinity over infinity, and then we can use L'Hopital's rule. This example says to evaluate, we have the limit as x goes to 0 from the right of x squared times ln of x. So what I'm going to do is I'm going to leave this ln of x in the numerator, so like here, g of x stays in the numerator, and then we're going to divide by 1 over the other functions. We're going to divide by 1 over x squared. So mathematically, this expression is equivalent to this one, and now we have ln of x. As x approaches 0 from the right, this graph goes to negative infinity. Here we have 1 over x squared, so I have the graph here, and as x approaches 0 from the right, the graph goes to positive infinity. Since the limit of the numerator equals negative infinity and the limit of the denominator equals positive infinity, this limit is of indeterminate form negative infinity over positive infinity. So we're going to apply L'Hopital's rule. The derivative of ln of x is 1 over x. To take the derivative of this function, we want to think of it as x to the negative 2, so then we get this as its derivative. So this function, you can think of it as negative 2 over x cubed. So now we're going to copy, dot, and flip this. Finally, we have a rational function, so we can evaluate the limit by using the direct substitution method. So we can plug in 0 and we end up getting 0. So that's our final answer. For this example, we have the limit as x approaches 0 from the right. We have 1 over e to the x minus 1 over x. So what we're going to do first is we're going to combine these into one fraction. They're going to need common denominators, so we're going to multiply this fraction by x on top and bottom, and then we're going to multiply this fraction by e to the x minus 1 on top and bottom. So we get this fraction. Next, I want to check the limit of the numerator and the limit of the denominator as x approaches 0 from the right. So I distributed the negative and got x minus e to the x plus 1, and the limit as x approaches 0 from the right, you get 0. Same thing in the denominator, I distributed this x, and so I got x e to the x minus x, and then again, the limit as x approaches 0 from the right, you end up getting 0. So this is of indeterminate form 0 over 0, so we're going to apply L'Hopital's rule. The derivative of x is 1. The derivative of negative e to the x is negative e to the x, and the derivative of this one is 0. For the denominator, remember we distribute the x to both, so you have x e to the x minus x. To take the derivative of x e to the x, we're going to use the product rule. So when we use the product rule, we get x e to the x plus e to the x, and then finally we want to take the derivative of this negative x, which is going to be negative 1. And when we check the limit of the top and the limit of the bottom, we get 0 over 0, which is going to be of indeterminate form 0 over 0 again. So we're applying L'Hopital's rule again. The derivative of 1 is 0. The derivative of negative e to the x is negative e to the x. We're going to next take the derivative of x e to the x, which we already did. The derivative of e to the x is going to be itself. And the derivative of this negative 1 is 0. So we could simplify this a little more, but we could also evaluate the limit, which I'm going to just do. X is going to 0 from the right. So for the numerator, you get negative 1. This term is going to go to 0, and this term as x goes to 0 is going to be 2. So our final answer is going to be negative 1/2. For our last concept in this lesson, we're going to talk about indeterminate powers. It says other indeterminate forms arise from limits of the form, the limit as x goes to a of f of x raised to the power of g of x, and show up as the following types. So you'll have 0 to the 0, infinity to the 0, or 1 to infinity. In order to compute limits of these indeterminate forms, I have steps written out for us. Step 1, we're going to set y equal to the limit. Then we take the natural log of both sides. Step 2, we're going to rewrite as limit of ln of f of x to the g of x. So this is a theorem from earlier in our textbook. And then we're going to use properties of logs and L'Hopital's rule to evaluate the limit. Finally, we're going to set ln of y from the very beginning of the problem equal to the simplified right side, and then we solve that resulting equation. This example says the limit as x goes to 0 of x to the x. I started the problem by saying assume that the limit exists, then we can represent it by, and again, since it exists, it's going to equal a value. So next, we're going to take the natural log of both sides. And I wrote a note using the fact that the natural logarithm function is continuous. We can rewrite the right side as the limit of and then ln of x to the x. At this point, we're using properties of logs to simplify the right side. So we're going to bring the power x to the front. So now we have a product of functions. So now we're going to rewrite this, just like we did on the left side of the back of the notes, as ln of x over 1 divided by x. So we have those graphs written out up here for us. I have ln of x as x goes to 0, approaches negative infinity, and the graph for 1 over x, as you approach 0 from the right, it's positive infinity, or 0 from the left, it's negative infinity. So this is going to be of indeterminate form, and we can apply L'Hopital's rule. The derivative of ln of x is 1 over x, and the derivative of x to the negative 1 is going to be negative x to the negative 2. Again, negative x to the negative 2 is the same as negative 1 over x squared, so we're going to times this by this reciprocal, or you can think of it as copy, dot, and flip. So when we simplify this, we get the limit as x goes to 0 of negative x, which equals 0. So our last step is we're going back all the way up to here, and we're going to set ln of y equal to 0, because these are equivalent. At this point, we're going to solve this equation. Because this is a natural log, technically it's log base e. So we're going to use e, and we're going to exponentiate by moving both sides of the equation up into the exponents. These are inverse functions, so e to the ln of y, those undo each other, and you just get y. And then e to the 0 is 1. And again, since y equals 1, and if we go up to the original problem and we set this equal to y, we can conclude that the limit as x goes to 0 of x to the x equals 1. For this example, we have the limit as x goes to infinity of 1 plus 1 over x, all raised to the x power. Since x is growing without bound, I want to look at this function right here. I have it graphed. As x gets larger and larger, you can see the graph is approaching a height of 0. So inside here, we have 1 plus 0, which is just 1, and then it's 1 being raised to the infinity. So it's of indeterminate form, 1 to infinity. So I wrote, assume that the limit exists. Then we can represent it by, and again, if it exists, we can set it equal to some value. Next, we're going to take the natural log of both sides. So we get the natural log of the limit as x goes to infinity of this expression. And since the natural log function is continuous, we can rewrite this part of the problem where we pull the limit to the outside and then we take the natural log of the inside. So we get limit of ln of this expression. By properties of logs, we can move this x to the front. This is a product of functions, so we can rewrite it where we leave this function on top and then we divide by 1 over this function. If we take the limit of the numerator, as x gets larger and larger, this is going to go to 0, so we get ln of 1, which is 0. And the limit as x gets larger and larger of 1 over x is also going to go to 0. So this is of indeterminate form, 0 over 0. Before we apply L'Hopital's rule, I want to manipulate it first. So right here we have 1 plus 1 over x. I'm going to rewrite it with a common denominator of x. So we're going to times this by x over x. And again, I just made a note that we're manipulating this to make it a little more convenient to be able to apply L'Hopital's rule soon. So we have ln of a fraction, so we're going to split this up as ln of the numerator minus ln of the denominator. And I'm just going to rewrite the denominator as x to the negative 1. So to apply L'Hopital's rule, the derivative of ln of x plus 1 is going to be 1 over this. The derivative of ln of x is 1 over x. And the derivative of x to the negative 1 is negative x to the negative 2. So we're going to combine this into one fraction with common denominators. So we're going to times this fraction by x over x, and we're going to times this fraction by x plus 1 on top and bottom. Next, instead of dividing by this fraction, we're going to multiply by its reciprocal. When you distribute the negative, these x's are going to cancel and you just have negative 1. I'm going to cancel this x and this x squared, and it just leaves an x on top. And we end up getting the limit as x goes to infinity of x over x plus 1. So here we have an infinite limit of a rational function. So the way we did this in a previous chapter is we divided by the highest power in the denominator, and we did that to top and bottom. Now as x gets larger and larger, this fraction goes to 0, and you just get 1 over 1 or just 1. Finally, we look back up to the original part of the problem, and it said ln of y, so ln of y equals 1. Again, when we exponentiate using base e, we go e, and then we raise both sides into the exponents. These undo each other and you just get y equals e to the 1 or just e. And since the original limit was equal to y and y equals e, we can therefore conclude that this limit equals e. So that's our final answer. All right, guys, thanks for watching.